Okay. Well, thank you for being here at the end of the long day and the first day of the OCP. So today, I'm here to talk about the Metaverse. My name is Young Paik. I'm a Senior Director in Product Planning at Samsung. And the Metaverse is kind of an interesting place. It's gotten a lot of press lately. It's an interesting thing. I will not be able to delve into any depth on it because it's just too big of a topic. The thing I wanted to mention is the Metaverse is going to be huge, right? There are a lot of companies that are going to be involved. Not a single company will be able to dominate this business, despite what you might hear. And what it will do is it will allow people new ways to kind of interact with each other. I'll be able to see movies with somebody that might be in a different country, a different part of the world, or whatever it happens to be. And there might be completely new business models. So there are new economies that are being developed right now specifically for the Metaverse. And the question is, what does this mean for storage? So let's take a deeper look at what the Metaverse really is going to need. And a couple of the things that we'll need is to be able to take things that exist in our general reality, what we know and can see and feel today, and put them into a virtuality. This includes people, right? When we interact with each other at a show like this, it's a very, very different feeling than when we're going to a show on a Zoom call or something like that, right? And I don't know about you, it's been 2 years since I've been at a conference the last time, and I can't even tell you how good it feels to be able to interact with people in person again. So I thank you all for coming to the show.
We thank you.
So, real people, and then being able to act in virtuality, maybe it's not quite as good, but it's something that we can do much more regularly and would be able to do virtually very easily. We might want to put real places in, right? We might want to be able to go to the Louvre or to a museum, a different part of the world, or some natural place, and we want to be able to see it even in virtuality, because I know my parents would love to be able to go to the jungles of Brazil, but there's no way they can handle that kind of a trip. We also want to put very real things, and in many cases, people want to take like a car and be able to co-design it with other people in this kind of a world together. So there are a lot of use cases for this kind of a world. They include telecommunications, they include smart cities, autonomous driving, and of course, digital twin and movies. So these are some of the goals that we have. Now, the question that many of you may have is, what does this have to do with OCP? Why does anyone here care about such a thing? So let's delve down a little bit and take a look at some of the technologies that we're going to look at. First of all, the Metaverse needs to be very compelling, right? So many of you may have either played Fortnite or seen your kids play Fortnite, and it's kind of a neat little world, very cartoonish. We want it to be more real than that. That's just not quite enough for what we really want. So we need to have a very compelling look and feel, and this will include requirements for computer vision and audio processing like we haven't seen before. Another thing is the ability to handle human-computer interaction. I want to be able to control things in this virtual world the way that I do in the natural world, in reality. I want to be able to pick something up. I want to be able to move it. And so HCI is getting to be a much hotter topic. We're going to see a lot more people developing things there. Communication, doing things using natural language processing. So I can interact with an AI to help me, find something. I can just give it natural language and say, help me find this thing and take a look at the results. Language translation, I often want to be able to talk to somebody, but sometimes there's a little bit of a language issue, right? And I work at Samsung, there's plenty of language issues at our company that some sort of language translator can help. And of course, we need to be able to do this at the edge, because I don't want to have to wait long periods of time to get my response back. And in fact, last night, I realized that there was a big problem because I told Alexa to turn off all the lights in the house, and Alexa told me my network was down, and it didn't know what to do. And so I had to go through my house, turning off the lights one at a time. And I got to tell you, it's a weird experience now, having to manually turn off all my lights. So I want to be able to do things closer to my house than I have before. The economy is actually a really new one, and it's one that's developing very quickly. Cyber currency is going very, very quickly. I think we've all seen the announcements on Doge and Shiba Inu and et cetera, all those cryptocurrencies. Advertising, as always, happens to be one of the biggest spaces. We're, of course, doing a lot of advertising today on the internet, but in the metaverse, it could actually hit new levels, and we're hoping that it's actually useful, right? So quite frankly, I am not as upset as some people when I see an ad that's actually kind of relevant for what I want to do. I just want it to be relevant. I don't want to see ads for something I don't care about. The last topic I put here, I kind of put here almost as a joke because I have no idea what an NFT is, but I keep hearing about them, and they seem to be very super popular. So these are some of the technologies that need to be developed in order to create the universe, metaverse. So the question is, can we start looking even deeper and finding some common ground with storage? So I'm highlighting a few of these things here: computer vision, NLP, natural language processing, language translation, and advertising. And I wanted to highlight them because these are things that I'm taking a look at with our customers today at a very large scale. So these are some very, very key technologies. And we can split them into two broad groups. Group number one are the use cases that require huge training volume, okay? What I mean by huge training volume is not a petabyte. It's tens of petabytes, and in some cases, hundreds of petabytes, all in a single namespace. So when I talk with companies who are used to dealing with large amounts of data, they are not used to doing this at high performance. And so this is a new category of problem that we're encountering now. And I'm actually working with a couple of customers on this very problem. The second one is one where the models tend to be huge. And these are the NLP transformers and recommenders that are out there. These models can get very large. And the reason why they get large is because you need to have higher accuracy. And these are very, very important for the development of all these technologies. So the critical issue here is that they want 1 trillion plus input parameters. And this will create very, very large models on the order of multiple terabytes per model. And we'll take a little bit of a deeper look. So to start with, let's take a look at the problem number one, the huge amounts of training data. In general, this is something that occurs when you're dealing with like lots of images, right? And here is kind of the evolution of a model through this sort of a platform. We, of course, have the early experiment. There's an AI scientist who said, I've got an idea for how this model should work. I'm going to put this into one GPU, maybe a couple of GPUs, and I'll just do it on a little bit of data just to test this out. At that point, they might find something that's good, and they'll scale this up to a new level. They'll be able to say, OK, let me do this on several GPU servers and still test it out. This is as large as they tend to get. They then hand it over to another team who will then begin to put this at large scale. And these large-scale projects can get, again, on the order of petabytes. And as I've said, we're working with at least one customer where we're dealing with hundreds of petabytes that need to massively transfer this data. And this, in general, also requires that many different AI scientists are working together on the same data set or at least the same storage. So how do we deal with this kind of a storage? If you go out there and buy your typical OEM appliance today, it's probably going to be extremely expensive for this kind of solution. So we started working with our largest customers to develop something that might be a bit more reasonable. So let's take a look at an example of what one of these tests look like. We have here a bunch of clients going to a rack of servers. And these are actually standard OEM servers today. And I just wanted to highlight that to give you a baseline. They have standard AMD CPUs, standard memory, standard everything, right? Everything's pretty standard on this. With this and some optimizations that we've been able to put together, we can get to about 275 gigabytes a second on 2.5 petabytes of data today. And that's pretty good, right? If you go out and you talk with people about this, they'll say that's really good performance. I myself don't like this. And as we've talked with our customers about the kind of performance they require, they actually want to go somewhat higher than this. And we've taken a look at how to get this performance. We've seen that file is very good at high performance at a small scale. Doesn't work quite so good when the scale gets very large. On the order of 100 petabytes, it starts to get much harder. With object, it's somewhat the reverse. We get not quite so good a speed, but we're able to scale up to very high levels. So I've started to take a look at how do you now design servers around this. Earlier today, EVP Jung-Yo Lee from Samsung presented Poseidon V2. This is one of our designs for this kind of a system. We have two designs here, Type 1 and Type 2. I don't want to go into the details of these because that's kind of beyond the topic here. But some of the key issues that we have taken a look at are, well, how do you design a server that can maximize capacity? And when you maximize capacity, you minimize operational costs. And when you do that, here's a version of the solution that we have. You have PCIe Gen 5 SSDs going to a CPU or a set of CPUs with high-speed memory DDR5 going to high-speed NICs on the back-end side. We haven't started doing the tests on this yet, but if we're able to get to 275 gigabytes already today, we're hoping to get much past that with this sort of a design with much higher capacities. And when we do that again, we can lower the costs. So hopefully by the next OCP, we'll have some good results to show you there. Another key issue, and this is one that is a little bit more of a detailed talk, I don't want to get too deep into this today, is this concept of CPU bypass. Today, a challenge in object storage is that the most common interface is S3, right? Everyone knows S3. Amazon's put it out for years. A lot of people use it. S3 is a great protocol, but it does use HTTP, which uses TCP networking. And as a result, when we get requests coming in general, we will actually go through the CPU, have it read the data from the SSDs, and then go out that way. So one of the tests that we've begun to conduct, and this is one that we're making a call for some help on, is the ability to bypass the CPU on that return trip. So the request to read comes in through S3 over HTTP, but the response will go directly from the SSD to the NIC and then back out into the network and onto the test server. So our belief is that we'll get a 45% increase with this. And this would be with more or less the same hardware, just slightly different software. And there are standards that we're going to have to work on as a community in all of these things. So now let's take a look at number two, the second challenge, which is the huge model size. And this is not something most people are aware of. If you take a look at the size of models today, they are getting bigger and bigger very, very quickly. And in 2013, they might have been, on the order of hundreds of megabytes, millions of input parameters. And what the AI scientists have found is if you increase the number of input parameters, you will get better accuracy. And they have started adding a lot of them. When I say a lot, we're looking at billions to maybe even trillions of input parameters. And when you get to that size, that can get to be multiple terabytes large. And the question is, how can you deal with that? When I used to talk with AI scientists about this exact issue, I would say, how do you decide how many input parameters to put into a model? And they said, I am misunderstanding it. It's actually backwards. What they do is they say, I've got a GPU. It's got 6 gigabytes of memory. I put in as many parameters as will fit in 6 gigabytes of memory. And they'll just do the best they can with what they got. And that's the way they scale things up. So one of the things that we've taken a look at is, well, how do we break down this model? And as it turns out, there are two different sets of input parameters that are possible here. Category 1 are the ones that require high bandwidth. And we will not move those from DRAM. They're very, very, they're intense. They require a lot of bandwidth. And so HBM memory that's in the latest NVIDIA GPUs and some of the AMD GPUs as well, they will stay in memory. There is another category that are sparse. A lot of these will actually wind up being zeros. So there might be hundreds of gigabytes of these things today in these recommender models. And we've seen that, right? We know how big these models are today, and they want to get even bigger. So one thought that we had is, why don't we change this around? And instead of taking these sparse input parameters and reading them out of the storage and putting them into the GPU for processing, let's do the initial processing inside the SSD itself. So that is something that we're undergoing right now. We're doing testing on this. It's very interesting, kind of the results of this. And what our goal is to take that model and break it so that we can make it multiple terabytes large and possibly trillions of input parameters. We want to get that accuracy up to make sure that people are able to get to the exact kinds of things they want to get to. Okay, so in the end, what are we talking about? We have essentially what's called an AI-enabled SSD. So instead of reading the data off the SSD, bringing it onto the compute platform and processing it there, we're going to send a command to the SSD, which will read the data, do the initial processing, and then bring that into the GPU or the NPU, whatever it happens to be, and then be able to process it. And this is the kind of work that we think is going to be very important for the development of AI in the future, and in particular for the metaverse. Okay, so I'm going to wrap things up fairly quickly just by saying the metaverse is, as I said, it's going to be huge. The examples that I've talked about are fairly simple, easy things for us to work on. We really are hoping that the community can get together to start working on these together. A couple of the groups that are at OCP that I hope that you'll start to participate in are the storage server groups. They're doing a lot of great work there. The server design groups as well. We're doing a lot of work with them to make sure that we can get the best data processing through those units. And there's a group here called the ODSA. They're working on the chiplet technology. And we're working on some test cases right now where we can read the data directly off the SSD and kind of process them in advance. So, with that, I hope that you'll enjoy the rest of OCP, and think about how you in what you're doing can kind of contribute to this sort of work, because we have a lot of things going on in the metaverse. Thank you.